Okay, cool. Okay, so everyone can hear me. Okay, this is good. Okay, so we're going to learn about bases today. And to understand what that means, let's first think about what it means to count and what numbers really mean. So you've probably heard of this before, the natural numbers. So this is just the symbol for the set denoting the natural numbers. Natural numbers. And these numbers are basically all the counting numbers. So it starts from 0 and goes up in ones, and you just keep on going forever. So it's just all of the integers without the negative numbers. So these are basically counting numbers. Okay, and yeah, the idea behind the natural numbers is that 0 is the smallest one, where it means you have nothing. And as you go on and on, you're adding 1 and you're counting upwards. Okay. So let's think about the symbols that we have for these numbers. We've used a 0 to denote a 0. And then when we go up by 1 count, we use the digit 1 to symbolize that. When we go up by another count, we use the digit 2 to symbolize that we've gone up twice. And then when we go up another count, we use the digit 3, and so on. And then we get to 8, and then we count more, and then we go to 9, and then we count once again, and then we get to 10. But this is interesting because this is not entirely a new symbol. So all of these digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9, they're all completely different symbols to each other. And we use them to basically, we use them as a visual symbol for how much we've counted. And it's interesting that when we get to the 10th number, we start repeating the symbols again, but we put them together so that we know that it means something else. We know it's not a 1 and it's not a 0. It's a 1 followed by a 0. So the point I'm trying to get at here is that hypothetically, we could use symbols to count that never repeated. So if I wanted, I could start with a 0, and then I could put a 1, and then I could put a triangle to mean the number after 1. And then I could put a star to mean when I count up again. And then I could denote the next count as an upside down triangle, and then the next one is a smiley face. Like, you get the idea, right? And yeah, can people see why this is just not convenient? Are we really going to memorize infinite amounts of symbols and remember what they mean? Yeah, too hard to remember. It's just impossible. It's really not a good system at all. Okay, but the cool thing about having this system where numbers repeat themselves after a while is that they're easy to remember, because essentially all we really have to do is remember the order of the first 10 digits, and then it makes sense to us what this means. It means that basically there's like there's been 10 counts and then we're on the 0th count. And then if I put an 11, it means that there's been 10 counts, but now I'm starting again. And when we put 12, it's like there's been 10 counts and now I'm on the 2nd count again. So really, we only need to remember the order and the comparative sizes of all the 10 digits. And our base system allows us to sort of start again from scratch when we get to different units of, different amounts of tens and hundreds. Okay, so I've been a bit vague, but basically what I'm trying to say is Okay, let me just scroll to a place. What I'm trying to say is right now, what we have is base 10 expression for numbers. So this is what everyone's used to. This is when we count from 1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 19, 20, 21, 22, ... And this is base 10. And it means basically that we only have 10 different symbols to remember, which were the digits from 0 to 9. And then the stuff just starts repeating. Okay, so to be really specific, let's think about what a number really means. Okay, so if I put this random number 8, 6, 4, 7, 2, then what that means is the last digit tells me how many I've counted in terms of units. So I've done 2 counts. If I look at the last 2 digits, so that's 72, then what that means is I've counted to 10 7 times. And then I've also had to continue counting another 2 times. So instead of having to remember 72 symbols, by putting the 7 in front of the 2, I'm just saying that counting to 10 has happened 7 times, and then I have to count another 2. Okay, now let's look at the last 3 digits. So 472. Well, what's happened is I've counted to 100 4 times. That's what this 4 indicates. And then on top of that, I've also counted to 10 7 times. And then the last thing that I've done is I've counted an extra 2 steps from there. Okay. Oh, I just realized people can't see. Yeah, so just to repeat, yeah, I've counted to 100 4 times, which is why 472 is the same as 100 times 4. And then on top of that, I've counted to 10 7 times, so plus 10 times 7. And then this last digit means on top of all that, I've counted another 2 steps forward. Okay, so that is basically what we call the base 10 representation of digits. And what I've done here by writing it as like 100 and then 10 and then ones is basically the base 10 expansion of a number. So these two are exactly the same amount, but this is just a really nice, clean, short, concise way of writing it. Okay, and do people want to guess, I mean, why is it called base 10? People in the chat, suggest to me why it's called base 10. I will wait for people to suggest things in the chat. Yeah, nice. Okay, so Yiming said, because there are 10 digits to use. That's exactly why it's called base 10, because this is the system where we've got 10 digits, which are the 10 distinct symbols, so from 0 to 9. But then at the 10th place, we start to repeat our digits and we start to reuse symbols and put a 1 in front of a 0. Yeah, okay. So just to remind ourselves, I'm just going to write, because there are 10 digits. And the digits are basically just the distinct symbols. Okay. Well, what is special about 10 though? So 10 is actually quite arbitrary. And I think many people argue that the reason that base 10 is the most popular base to look at numbers in is because we have 10 fingers. So I think someone told me once something like, if we had 11 fingers, which is a prime number, then civilization would have developed at like a way faster rate. It was either way faster or slower. I can't remember. But the idea is that 10 is a composite number, which has implications for number theory. But yeah, I don't know anything else. But anyway, yeah, it's pretty interesting that we're so accustomed to seeing numbers in base 10 that we don't even think about what numbers mean. So what digits mean when you put them one after each other. Okay, so as people may have already guessed, what we're going to do is we're going to look at other base systems. So, okay, I'm going to start writing up here. Let's look at, okay, let's do another base 10 example just to make sure we all get the idea. Base 10. Oh yeah, I didn't even, whoops. I just realized that I didn't finish this example. So I didn't even finish the 8, 6, 4, 7, 2. So we only expressed 472 in its base 10 expansion. But in general, what you do to express any number in base 10 expansion is you take the last digit and you multiply that by 1, because the last digit tells you how many ones. And then you take the second last digit and you multiply that by 10, because the second last digit tells you the amount of tens. And then the third last digit tells you the amount of hundreds. And then fourth last, not surprisingly, tells you the amount of thousands. And then the fifth last tells you the amount of 10,000s. Yeah, so as you can see, as you move this way on the number, you just increase the amount of zeros that the number represents. So in general, if I had a number that was like, okay, let's say, hang on, I'm gonna move the board. Okay, so in general, let's say I've got how many digits? So in this number, I had exactly 5 digits, right? So my largest digit, sorry, the digit with the most heavy weighting, or the one that represents the largest number, represents 10,000, which has 4 zeros, because it was like 0 zeros and then 1 zero, and then 2 zeros for the hundreds, and then 3 zeros for the thousands, and then 4 zeros for the 10,000s. So you just increase a zero every time. So in general, if instead of writing numbers, I'm going to express the, like if I'm going to say this is a random number, one second, A2, A1, A0. All right, okay, let me try and explain what I've done here. So here I've just written a general number. And instead of writing numbers, I've replaced them with the letters A0 all the way up until AN. So this blue mess here represents a sequence of digits. So each of these things is from 0 to 9. Each of these things is a digit. And I'm just, oh, you can't see that, sorry, yeah. Each of these things is a digit. And I'm saying that I've got this general number which has n plus 1 digits. N plus 1 because the 0th one is also a digit. And in general, if we want to express this in base 10 expansion, then that's the same as saying, remember what we do? We take the last digit and we multiply that by 1. A0 times 1. Take the second last digit and we multiply that by 10. Take the third last digit, we multiply that by 100. by the way, we add them together, of course. And then we keep on going, right? So we add more stuff in between. So all these dot, dot, dots, I don't want to write them all out because I don't know how big n is. And then eventually I'll get to this place here, an minus 2. Okay, now I have to multiply this by some multiple of 10, but the question is, how many zeros do I have? Okay, well, let's think about it like this. The rightmost digit represented 0 zeros. There are no zeros here. Second last digit represented 10, which has 1 0. Third last digit represented 100, which has 2 zeros. So you can kind of see that the number of zeros matches up with the subscript. So the little number that I'm putting next to the A. So 2 matches with the number of zeros that it holds. 1 matches with the number of zeros in that term. So in general, an minus 2 is going to be weighted with 10 to the power of n minus 2. So remember that 100 is 10 squared and 10 is 10 to the 1. So the power also tells us how many zeros are in that number. And because I don't want to actually write n minus 2 zeros, I'm going to write 10 to the n minus 2. Okay, cool. So this is just the general expression for a number with digits an all the way up until a0 in base 10 expansion. And then the last term is an times 10 to the n. Okay. Yeah, can people write in the chat if they get what I've done here? Okay, great. Very good to hear. Okay, cool. Now let's move on. I think we've got a pretty good understanding of what base 10 means, which is good. And I know you probably have seen this all before, but it's worthy of being recapped because now we're going to look at different bases. So let's look at base 3. Base 3. Yeah, because like I said, 10 is quite arbitrary and it's like, why 10? And the answer was probably because we have 10 fingers. So that's the most commonly used base, but we could have done base 3 as well. And in the base 3 setting, remember that 10 had 10 symbols. And so we had 10 digits for base 10. Now in base 3, the idea is that we only need 3 symbols. So if I wanted, I could use a triangle to denote the empty count. So the number which represents no counts at all. I could use like a square to represent the first count. And then I could use like a circle to represent the third count. Sorry, the second count. And there are only 3 symbols here. And I don't need any more because then after that, my system can continue. So then I could say that the next number is represented with a circle followed by a triangle, which means that, I could also do like a square followed by a triangle. And what this means is that I've done this amount of counts. So I've done 3 counts 1 time. And then after that, I've done no counts because remember the triangle means no counts. What does this one mean? So this one means that I've done this many counts. So 3 counts because we're in base 3. And I've done that this many times where the circle just means 2. So I've done that 2 times. And then on top of that, I've done 0 counts. Okay. I could also do square followed by circle, which means that I've done 3 counts because we're in base 3, 1 time because I've got a square. And then I've, on top of that, done 2 counts. Yeah, so as you can see, it pays to have a really good understanding of base 10 so that we can understand what it means to count in different bases.
We could have also used the numbers 0, 1, and 2, right? As the
Yeah.
symbols.
Okay, let's use 0, 1, and 2. Okay, so here what we're going to do is we're only going to use the first 3 digits because the other digits aren't needed anymore because we're in base 3 and we only need 3 distinct symbols. Okay, so basically this is how counting works in base 3. We start with 0, and then the next number is 1, and then the next number is 2. Does anyone want to guess what the next number is after 2? We can't use 3 because we don't have a symbol. Exactly. Yeah, it's just 10. And then 10 plus 1, and then 10 plus 2. And then what's the next one? Yeah, exactly. Actually, okay, Finn missed out on a critical number, 20. Yeah, cool. So 20, 21, 22. Okay, and here's where it gets interesting. We can't go to 30 because there's no 3. So yeah, people have got it. It's 100. So now we've got another place, and then 101, and then 102. And then we go to 110, 111, 112, etc. Okay. So in general, if I have, again, an arbitrary number with these digits, A2, A1, A0, then if I want to express that in base 3 expansion, then what that means is I've got an lots of 3 to the n plus an minus 1 lots of 3 to the n minus 1 plus an minus 2 lots of 3 to the n minus 2 plus, whoops, no, I drew too low, plus dot 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 because of all the dot dot dots in the middle here. I just realized that the dots aren't showing up. Dot dot dot. Yeah, okay. And then plus 3 lots, or A1 lots of 3, and then plus A0 lots of, well, 3 to the 0, but really 3 to the 0 is just 1. So I'm just going to put A0 here. Okay, cool. So that's the base 3 expansion of a number. And then we're going to generalize it even further and just say that for any B, we can count in that base. So in general, base B expansion. So if I'm going to look at the number, if I'm going to look at the number 2876 in base B, then what that means is that I've got 2 lots of B to the 3. I've got 8 lots of B to the 2. I've got 7 lots of B to the 1. And then I've got 6 lots of B to the 0. And let's do the general version again. So an minus 1 dot 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 a1 a0. Again, you take the biggest number and you do b to the n plus second biggest times b to the n minus 1 plus dot 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 plus a1 lots of b and plus a0. So a0 is always the unit. Okay, so that is how you express numbers in different bases.
Yeah, and it's implied that the b is bigger than 8 when you use the 8, yeah, people.
Oh, yeah, that's true. So in general, sorry, wow, my throat. Yeah, remember that what base B means is that we're using B distinct symbols. B distinct symbols. So if we're gonna use the same digits that we're already used to, 0 to 9, then that means that the digits go from 0 to B minus 1. Yeah. So you're not going to have any digits that are bigger than B minus 1. So remember in base 3, we only used 0, 1, and 2 because we only need 3 symbols, but we start from 0 just by default or by convention. So whoopsies. Yeah, so as Michael pointed out, I actually used an 8 here in this number. And this wouldn't make sense if the base I was using, if B was smaller than 8, because I wouldn't need the 8th digit as a symbol. I would only need 0 to B minus 1. So this number implies that B is greater than 8. Yeah. So instead of 0 arrow B minus 1, let's just be specific. The digits go from 0 to 0 digits to B minus 1. Cool. Okay, now we can finally do a bit of proof. Everyone's favorite. Okay, so where do I go on the whiteboard? Okay, so theorem. So the theorem is that every number in the naturals can be, so key can be, and then second keyword, uniquely, can be uniquely expressed in base B, where B just needs to be another natural number. So technically our base can be anything, but I really hope someone doesn't tell me to express something in base 32 because I don't really want to remember 32 symbols. Okay, and yeah, remember that B is just basically the number of symbols we have, and B is, in this general theorem, a natural number. So we could choose it to be 3, we could choose it to be 5, could choose it to be 7, and we can also choose it to be 10. So 10 is the base that we're used to. Okay.
Right, so just be careful when you're stating the theorem. Make sure you state the the base first, yeah? So once the base is agreed on, then every number has a unique expression. Otherwise, it might seem like they can be, the bases could change and people could be uniquely expressed in the same digits in different bases or something.
Okay. Yeah, okay. Let me just restate that. Let's just make that a little bit clearer because, yeah, as Michael said, no one knows really what I mean by unique, but I mean unique given a base. So, okay, let's just write the proper result. I'll write it in dark blue next to it. So let b bigger than 1 be a whole number in n. Yeah, okay, so that's something I missed out. You can't have base 0. Okay, then any number n in the natural set can be expressed uniquely let me scroll down in form n equals a m e to the m plus ... So a0 b to the 0. So basically, remember b to the 0 is just 1. So I can really just get rid of that because it's 1. Okay. And also, by the way, like we looked at earlier, the digits have to be between 0 and b minus 1. Because we only need b symbols. Okay, and when I say I just mean just an arbitrary index. Okay. Okay, yeah, so I guess Bright raised a good point. We do already know the alphabet and we already know the order of the alphabet. So technically it wouldn't be too hard for us to express numbers in base 26 because everybody is pretty sure of what the order of the letters in the alphabet is. Okay, anyway. So yeah, this theorem basically says to us that every number, every counting number, so given a base, say I've already set my base. Oh yeah, and Finn said you can combine letters and numbers. So we could say, go from 0 to 9 first, and then follow that by the alphabet. And then what happens at base 37? Yeah, we'd have to introduce a random another symbol. Okay, so back to this. This theorem is basically telling us that every counting number can be expressed uniquely as some sequence of digits, am minus 1, ... a1, a0, can be expressed uniquely as, yeah, a sequence of digits, and that there is no other sequence of digits that can give you the number n. So remember that this is just the expansion of the number with these digits. So actually, if you consider these as like digits making a number, then this is equal to n, but then this is also equal to n because that's the expanded form. Yeah, and so the theorem basically says that this sequence of digits is the only sequence of digits that you can use to express our number n. And that might seem obvious to you, especially because we're used to base 10, but it requires a little bit of proving. Like it's not immediate, especially if you've never seen a counting system before, that you can choose only one set of digits, A0 all the way up until AM, and multiply them by powers of b to the m to get a number. Like there's only one way to do this. Okay, so let's get to the proof. All right, so there are a couple things to prove here, and we're going to basically break it down into 2 steps. So again, like I did before, can be is a keyword because that means that there exists digits A0 all the way up until AM that can be used as the coefficients of powers of b to give us a number. So there exists digits. And then the second key part is this uniquely part, because that says that no other digits, no other sequence of digits gives you this number, gives n, which is the number that we're interested in. Yeah. So I hope that this is obvious to everyone in base 10 at least, because I think we can all agree that 100 can only be expressed as a 1 followed by a 0 followed by another 0 and nothing else. And in fact, that every counting number has a representation in digit form. Okay, so we'll just prove it in the general case. Okay, so I'm going to start with existence, which is the part that's can be. So it exists. There is a bunch of sequences. A bunch of digits. Okay. So the way we do this, and I said the way because it happens to be the unique way, we define m to be the largest power as largest power of b, so that b to the m remains smaller than our number n. So it's basically like, how many multiples of b can I fit into my number? Okay. And then basically this tells you how many digits we're going to have. So in the case of 102 in base 10, well, the largest power of 10 is 2 that fits into that number. So only 100 is less than 102. And so that immediately tells me that there are going to be 3 digits, A0, A1, and A2. Yeah, anyway. And then the obvious next step is, I'm going to move a little. So, oh, I'm drawing so big suddenly. Obvious next step is can people see this? Where is my writing? Ah, okay, I'm writing up here now. So let A subscript m, remember that these are the digits, be the largest number such that AM lots of b to the m is less than my number. Okay. And you guys can check this, but AM will automatically be less than b. I don't need to say that as an extra condition AM has to be less than b. because it just will be less than b based on the fact that b to the m is the largest power that's less than n. So you can check that in your own time. This already gives us that am will be less than b. Okay, so now we've got the first digit. We've got like the digit with the largest weighting. Okay, now the idea is we look at, so we've got the largest digit. So now we look at n minus am lots of b to the n, because the idea is we're trying to express what's remaining in the number in digit form. So we need to look at what's left. We've already accounted for the biggest bit, am lots of b to the n, and we want to look at the rest. So what we do is basically repeat the entire process again. So this is basically like our new number. So let n minus 1, oh, okay, sorry, not let n minus 1. Okay, we don't want that. We're not really repeating the same process because we're going to be looking at lots of b to the m minus 1. Yeah, we can't ignore this because we need to say how many lots of b to the m minus 1 fit in here. Anyway, so let's just ignore all this. Anyway, so basically what we do is let am minus 1, which is the next digit, be the largest number such that I hope people can guess what I'm going to write, but am minus 1 lots of b to the m minus 1 remains less than our number n minus am b to the m, which is basically just the residue. So what's less? Oh yeah, less than or equal to, my bad. Thank you. And up here as well, less than or equal to, because for example, in 100, yeah, in 100, my m would be 2. So the largest power would be 2. Yeah, whoops, these all need equal signs. And then 100 is just 10 squared. So yeah, I want equality to be okay as well. Anyway, where am I? Okay, cool. So now we have the next digit. So far we're basically forming a number. We've started with am in the mth place, and then we're putting in am minus 1. And then we're gonna have to keep on going and find our coefficients all the way down to a0. We've already found this one and this one. Okay, so now what we're gonna do is look at again what we have left. So again, we've looked at the bm bit. So we've already found the digit which gives us the lots of b to the m. We've also already looked at the second last digit, or the second digit. So we've already seen how many lots of b to the m minus 1 fit in there. So that's why I'm subtracting these, because I want to look at what's left. Okay. So the next step is let am minus 2 be largest num such that, so st just means such that am minus 2 b to the m minus 2 less than or equal to this. So it's basically how many lots of b to the m minus 2 fit into my number without all its bigger components. Okay, and we basically just keep on doing this. So dot, 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 until you let A0, the units, to be largest number, such that, and can people guess what's going to happen here? A0 less than or equal to n minus a m b to the m minus a m minus 1 b to the m minus 1 minus dot, 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 all the way up until minus a2 b squared minus a1 b. Yeah. Okay. So, yay. You can check that after we do this entire process, then basically by design, we've made this number. Then n is equal to a m b to the m plus a m minus 1 b to the m minus 1 plus dot, 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 plus a1b plus a0. So yay. So that means that we've found some coefficients ai. So we found some digits ai that can be put in a sequence to give n. So I can express n in terms of digits a m minus 1 all the way up until a0. So this is the digit form. This is the digit form of n. Okay, yay. So that means we've answered the first part of the question. We've proven now that any number can be expressed in some digits. Okay, and now we want to prove uniquely. So we want to prove that there are no other digits that give us this number in base B. Okay. Where do I write? Okay, I am going to write over here. And I need to get my bearings on my whiteboard. Sorry, 1 second. By the way, if people have questions, please put it in the chat and I'll respond. So if there's any bit that doesn't really make sense, I'll respond when we can. Where am I? Ah, there I am. Okay. So now we're going to prove the next bit, which is uniqueness. Okay. Okay, we're going to do a trick, which is quite common, but okay, so let's prove this by contradiction. So assume by, sorry, I'm writing on the tablet, so I have to keep on zooming in and out. Assume by contradiction. Assume by contradiction that n is equal to, what letters should I use? I'll just use A again. So A, M, B to the M. I'm writing it in expanded form, plus A, M minus 1, B to the M minus 1, plus dot, 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 plus A0. And it's also equal to some other digit representation. I'm going to make these new digits be labeled with C. Cm, B to the M plus C m minus 1, B to the M minus 1. plus dot, 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 all the way up until the units digit, where basically there is some digit that's different. Oh, actually, you know what? We don't even need to do contradiction. Basically, assume no need for contradiction here. Just assume that n can be expressed in 2-digit forms. So you can express it with all these A0s, sorry, all these AIs, and you can express it also using digits C. So I'm just going to write where 0 is less than or equal to AI and CI less than or equal to B minus 1, because that's the only condition we have on digits. So the way we're going to prove uniqueness is by showing that AI equals CI for every index. We show AI equals CI for all the indices going from 0 up until m. So all of these AIs are equal to CIs. And I hope people can see how that shows that the digit representation in base B of n is unique. Okay, so what we're going to do is n minus n. Okay, can people tell me what n minus n is? I'm not even going to wait for a response. So n minus n is 0. Okay, awesome. I'm going to use this nice opportunity to put both of my different digit representations in one place. So I'm going to subtract the first way of expressing n. So am b to the m plus am minus 1 b to the m minus 1 plus dot dot plus a0. Cool. And then I'm going to subtract. So this is one copy of n. I'm going to subtract another copy of n. So that's going to be this part. Subtracting cmb to the m minus cm minus 1b to the m minus 1. And then keep subtracting the rest of the number until I subtract the units bit. Okay. So basically, that's the left-hand side. And because I've subtracted the same number from itself, that's all equal to 0. Okay. Now let's do some factorizing. So I'm going to factorize the b to the m terms. So I've got am minus cm b to the m plus am minus 1 minus cm minus 1 b to the m minus 1 plus dot 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 plus, well, there's going to be a1 minus c1 plus, well, I mean, I could say, wait, no, I'll just continue. So plus a0 minus c0 is equal, oh wait, there's a b, whoops, forgot about that, equals 0. So all I've done is just expanded the factorized the left-hand side. And I've got this thing here. Okay, let me just do some dividing so that we don't get confused. Okay. Proof. Oh man. This is what happens if I try and write on my laptop. Okay, anyway. Okay, so I'm going to very strategically bring the units digit to the other side. So instead of this, I'm going to say that this whole thing, so everything to the left here, everything here is equal to the negative of this, because I'm subtracting A0 minus C0 from both sides. So to negate it, it's just C0 minus A0. I hope people can see what I did there. Okay. But then that is basically the same as me saying, okay, got to zoom in again. So that's basically me saying that, well, I'm actually gonna, oh, I'm writing down here now, I guess. Maybe not. Okay, I'm gonna factorize out a b from everything on the left. So we can see that everything here has at least one multiple of b. So that means I factorize out the b and I take a b away from each of the b's. So that means n minus 1 instead of m. Plus dot, dot, dot. I can't be bothered to write the rest. Plus, and the last one here that I can factorize is a1 minus c1. Okay. So b outside of this mess is equal to c0 minus a0, right? Okay. So that means that this side, this entire left-hand side is a multiple of b. Okay, cool. But then my right-hand side, well, each of these numbers, a0 and c0, is greater than or equal to 0, but they're also both less than or equal to b minus 1. So does someone want to tell me what we can conclude? So if my right-hand side has numbers which are less than or equal to b minus 1, but then this thing is also supposed to be a multiple of b, so equivalent to this multiple of b, then what can I conclude? Okay, so maybe I'll reframe the question. What are the possible values of A0 and C0 that can give us a multiple of B when we look at C0 minus A0? Okay, how about this? I have these numbers A0 and C0, which are greater than 0, greater than or equal to 0, and they're less than B. So what's the biggest possible number that I can get from C0 minus A0 within these constraints? What's the biggest possible value of this thing? Can people write in the chat, by the way, if they're following at all? I want to know if the silence is due to not knowing the answer or due to not following. Okay, yay, someone said something. Thank you, Nathan. C0 equals A0. That is the right conclusion to draw. That is eventually the conclusion that I wanted to arrive to. But okay, let's go through this. So I'll answer my own question from before. I asked you, what is the biggest value possible of C0 minus A0? Well, C0 and A0 can only have values between 0 and B minus 1, right? So the biggest possible thing that I could have is if I set C0 to be the biggest possible, and if I set A0 to be the smallest possible to get the biggest possible value of this. Okay, but if I do that, then that means I'm setting C0 to be B minus 1, and I'm setting A0 to be 0. So the biggest possible value of C0 minus A0 is B minus 1. And then what's the smallest possible value? Someone want to tell me what the smallest possible value is? Yeah, so Nathan's got it. So it's 0 smallest possible, and we can do that just by setting A0 equal to C0. Okay. So Nathan, especially because Nathan got the answer, do you want to tell me why we can conclude from this, together with the fact that C0 minus A0 is supposed to be a multiple of B, that A0 equals C0? Oops. Oh no, didn't mean to do that. Oh, sorry, I have to refresh my page. Okay, awesome. So Nathan said, because C0 minus A0 is a multiple of B, that's true because we've set it equal to this thing, which is a multiple of B. But then C0 minus A0 can also only take values from 0 to B minus 1. And the only multiple of B in this set of numbers from 0 to B minus 1 is 0. So together with being a multiple of B and being between these values, what? Sorry, I'm trying to connect to the thing. Where are we? Where are we? Okay, yeah, so, sorry, I had to refresh my whiteboard again. I'll just write here for now. Okay. Yeah, okay, so basically all I wanted to write there was multiple of B, right? So
Wait, hold on. Couldn't C0 minus A0 be negative?
oh yeah, you're right. Okay. So well, here what I did was C0 minus A0 is B minus 1 by setting C0 to be the biggest number and A0 to be the smallest number. But I could also do the opposite to get the most negative number possible. I could set A0 to be the biggest, C0 to be the smallest. So I would just get the negative of B minus 1. But the conclusion is still true. Between these values, from negative B minus 1 up until B minus 1, the the only multiple of b is 0. So, so basically this condition together with this range condition gives me the fact that C0 minus A0 equals 0, which means C0 equals A0. Yay. Okay, so let's continue now. What does that mean? Is my whiteboard back is the question. Okay. So that means that, well, I'm just going to rewrite this thing, but now I can replace this thing with 0 because we just found that it's equal to 0. So that means that B, where's my writing? Oh, yay. Okay, so that means B outside of that mess, AM minus CM, lots of B to the M, plus, and then the last thing I had was A1 minus C1. So that means that this whole thing is now just equal to 0. I'm literally just rewriting this, but now we have C0 equal to A0. Okay. So, well, since now I've got a 0 here and I've got some multiple of B, well, the only thing that multiplies with B to get 0 is 0. So that means that this thing in brackets is also equal to 0. So now I can just, I'm going to cross out the B. So this thing is now equal to 0. Okay. Do people see what to do next? Repeat. Yes. Good job. Yeah. So Nathan said we just repeat. And that is exactly what we do. This is the exact same situation we had before. And so we can just repeat, subtract everything, subtract the units from both sides. Zoom out. Sorry. So that means instead of this equals 0, we're going to have plus dot dot plus A2 minus C2B equals C1 minus A1. But then the exact same reasoning applies to say that C1 minus A1 is 0, because the left-hand side is a multiple of B, and this side can only take values between minus B minus 1, C1 minus A1, and B minus 1. Whoops. B minus 1. Yeah, okay, so same reasoning applies. That means that this is equal to 0, so C1 equals A1. Okay, yay. So as you can see, if we just keep on repeating this process, then eventually we're going to get, everything. We're going to get C0 equals A0, C1 equals A1, C2 equals A2. Oopsies, move. And we'll get eventually also the biggest ones, so C M equals A M. And so that basically means that that basically means that all of our digits are the same. So given 2-digit representations of n, the digits are actually the same. And so this expression is unique. Yeah. And okay, so one detail is that, well, this was made easy because I have m plus 1 digits. So I've gone from 0 to m. And you could ask, why aren't we checking some digit representation where there's more or less than m plus 1 digits? But in my existence, okay, well, I guess we can just show that there can't be any more digits. So, I mean, b to the m was by definition, where are we? Yeah, b to the m was by definition the largest power of b, so that b to the m is less than or equal to n, right? So let's say that there were more digits.
All right, hold on a sec.
Huh?
So I don't know if that applies to the uniqueness part, because we haven't proved that in every expression that b to the m is the largest part of n. But the thing is, your argument already shows that every digit will be the same no matter how many like if it keeps going on, if there's more c's, they'll still equal all the a's, right? It's just the a's are 0.
Oh, true. Yeah, okay.
Yeah. Yeah.
Okay, I see. Yeah, so
Yeah,
if
you're already done.
if there were more C's, then you just tack on extra digits to the A's, but you make the first few 0. Okay.
Yeah, so for that proof, so the existence part, I think most people should be able to believe even without seeing that, right? They're kind of convinced that there should be some way to represent them in some base, but I think the proof helps you get used to a bit of the notation. I mean, if you think about it, you probably don't, some of you don't know what a polynomial is, but that's about as complicated as algebra notation gets, just like powers of some b and then coefficients a sub m in front of the b's, yeah? It doesn't really get much more complicated than that in terms of notation. The base expansion is just like a polynomial in b, so if you can kind of get used to that, you won't ever be intimidated by notation. And you can see that the uniqueness part of it is actually a nice argument. But you might not appreciate the argument if you got lost in the notation, right? And so I think it's important to try to learn the notation, even if you're convinced that it's easy, that the representation exists, okay? Because then when you're trying to prove it's unique, which I think is not easy, you won't get bogged down by the notation. Okay, that's very good.
Yeah, so that was the end of the proof for the theorem that every number has a digit representation and it's unique in base B.
Yeah, so I guess for time considerations, we might skip the converting from base to base examples. I think a lot of people can read that on their own, or if they really want, I can send you a video of having done base to base. I think you even do this at school, so we can skip that. But I guess the question maybe you can think about while Ayush is preparing to start his mod arithmetic thing is, maybe we've already done this in class. How far can you count to on your fingers? If you have 10 fingers, what's just the largest number you can count to? Bright says 99. All right.
99.
Excellent. Well, why is that? Yeah, Nathan's getting more close. Sensitive fingers. I can express. Oh, look at him. He's back.
Hi,
Oh no.
Bright.